Hello everyone, welcome back. So this time we're going to be doing a 3D equilibrium problem. Don't freak out. I'm here to help you. And also, this is a video. Honestly, you can pause and take as much time as you need. So, no need to be worried. So, let's look at this. So we see four forces and the geometry are shown. So we have a rope here, a rope here, a rope here, and a weight of 300 pounds. And we want to know what the tension developed in the cables AB, AC, and AD are. Okay? And it gives us those in various ways. You see we have angles for one to the Y, Z, and X axes. And then we have an angle down to the Y-X plane, and then an angle from that projection line to the Y-axis. So we're going to have to work with these in various ways. So, what's your plan of attack? Well, first off, you need to write these forces in Cartesian vector form. You need to break them up into components. You can't just use these angles. You've got to break it up and figure out what the components are. Get a unit vector, and then multiply the unit vector by some variable, TB, TC, and TD. You got three equations, you have three unknowns. You should be able to solve, and hopefully if you're lucky, you can avoid some painful algebra. Not always possible, but it might be. Okay, so with that in mind, I'm going to pause here. I want you to go and try it on your own. So I'm going to count to 3, and by that point I hope you paused, tried it, and then you come back and we'll talk about it together, okay? So 1, 2, skilly. Here we go. So solution. Now this goes a bit too quickly, so I want to explain where all of this came from. So first off, this one's the simplest. TB, it was just along the x-axis. So if we're breaking it up into components, it has only an I component. It's only going along the positive x-axis because ropes can pull, they can't push. So this arrow has to be going away from the little ring that's holding everything together. Okay, TC, we're given two things here. We see we have an angle down to the xy plane, and we have an angle from that projection vector over to the y-axis. So if I look at this now, pull my pen, if I look at this, what I do first is I break it up looking at it this way. This is TC, and I have a 60-degree angle. And then if I look at it, I have the z-axis right here. This is the z component, or if we're going to use these, the k component of my TC vector. So this would be, make sure I do my angles here, TCZ. And this one right here we usually call TC prime because it's on the XY plane. That's right there. Okay, now if we solve this, what we get is that TCZ is going to be equal to my TC times which trigonometric function? Well, it's opposite over hypotenuse, so sine of 60. Well, that one's awesome. We've already solved that one right there. And then TC prime is just going to be different. It's going to be TC cosine of 60. Okay, so that's not too terribly bad. Now we have a second triangle, this one right here. We have to break that one up too. Our hypotenuse has changed. It's now TC prime, which we have already solved for once, and we have to figure out the rest of the signs. So this one right here would be TCX, which is going in the negative I direction. That's why this is negative right here, because it's going that way. And then we have TCY. Be very careful with this, because when you rewrote this, you might have just been tempted to say, well, the bottom one is always the X. That is my initial idea, just because that's what I'm used to. The bottom is X right here. The side is Y. Be very careful. This was X, this was Y in this particular case, because of how we drew it. So think about that. Okay, so if I want TCX, it's going to be equal to TC prime sine of 30. And then our TCY will be the opposite with cosine 30. And that's where this came from. So you see the cosine of 60 came from our initial one, and then sine of 30 and cosine 30 came from our second triangle. Cool? Hopefully. Maybe not. Okay, now let me erase all of that. You can pause things if you need more time to look at it all. Now, the second one is actually much simpler. We have this right here, and it gives us angles to all the axes, which means we can use those awesome angle cosines. The one thing we have to be very careful about, though, is with our y-axis right here. Because we don't use the angle from the negative axis, we always use the angle from the positive axis. Or you just have to be very careful with your sign. So in this case, I'm going to be very careful with my sign and say cosine of 120. So with that in mind, we have, let's make sure I get all the angles here. Yep, okay. This one right here should be cosine of 120. This one right here should also be cosine of 120 to the y-axis. And then this one right here should just be 45 degrees, if we have everything correct. Which it looks like I think we do. Okay. Hopefully. And you can see that they got this right here. But the issue is not with the problem. The issue is simply with my reading. This is just it's solving for TC. I forgot that this is not TD here. I was already jumping ahead. This is TD, and as you can see, they use cosine 120, cosine 120, cosine 45. Be careful, people. You jump ahead of yourself. Things mess up. So with that in mind, we solve for everything. We have all three of these in their Cartesian form, which is great, because then we can break it up into the I, the J, and the K components. So we have all the I's right here, all the J's right here, and all the K's right here. And it's up to you to decide how you're going to do it. My advice would be to solve the J and the K components first, because there's only two of them, less algebra that way. And then you can solve the I components after you've already solved for those. It'd be very simple that way. So, you decide how you're going to do it. This is the vector equation. And you can do this if you want to, but go ahead and break up into three scalar equations. Here's equation 1, 2, and 3. And then after this, you can solve all three of these equations. Now take some algebra, but look at it right here. There's only two equations, two unknowns for the y and the z components. That's probably the easiest place to start. After that point, you can jump up here. The second thing that can make this easier is you see that 0.866 and 0.433. It's fairly simple to get this in terms. Like I don't have to solve just for TC. I can solve for 0.866 TC or 0.433 TC and then plug that in. Just easier ways of going about it. Now, if I solve, I get that TC is 203 pounds, TD is 176 pounds, and TB is 139 pounds. Okay, so with that, we have solved the problem. So remember, it's just three equations of equilibrium. And be very careful when you're working through it that you don't confuse yourself by writing down the wrong thing. This was completely correct here. I was just thinking that we were on TD. So apologies for the little mix-up there. Okay, with that, I hope this helped you, and I'll see you all next time as we do some more examples. Bye-bye.